Polling long LLM jobs wastes time and breaks easily. A FastAPI webhook receiver lets async results land cleanly and update job state. This is the pattern you'll be able to implement by the end, which verifies a signed callback and safely updates a job with its result. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Long LLM tasks are common. Think batch generation, long-form summarization, or async fine-tuning. Providers often return a job ID immediately and deliver results later. Developers either poll repeatedly or build a callback. Polling costs, cycles, and latency, and makes systems fragile when networks hiccup. A webhook gives you push delivery. Success means fast acknowledgements, verified authenticity, and a durable job record that reflects the final result. That makes dashboards accurate and downstream jobs reliable. At a high level, we will build a small FastAPI receiver that accepts callbacks, verifies an HMAC signature and timestamp, deduplicates or orders events, and persists the final state. The example stays simple so you can map it to your real infra without mystery. Now we will start with a minimal receiver. This snippet creates a minimal FastAPI webhook that records LLM job updates. The app object is a FastAPI instance that will host routes. The dictionary named jobs serves as an in-memory store keyed by job identifier. The function LLM webhook reads the JSON body from the request, extracts a job ID and status, and stores both with a simple timestamp. Returning an OK flag and a scene count provides immediate visibility that the receiver is wired. If your provider retries, keeping this handler lightweight ensures fast acknowledgements. The printed jobs tracked value confirms the receiver is ready without creating any jobs yet. Next, we add signature verification and replay protection. This code adds HMAC SHA-256 verification to authenticate webhook callbacks with a timestamp. The constant secret holds your shared webhook signing secret, and SKU limits how old a request can be to prevent replay. The function validSig builds a message as timestamp.body, hashes it with hashlib.sha256 via hmac.new, and checks freshness plus constant time equality. A tiny body and generated SIG simulate a real provider post, so you can validate the logic offline. Lowering SKU tightens replay tolerance, but risks rejecting slower networks. Increasing it is safer, but widens the replay window. The printed signature valid value confirms the signature and age checks pass. Now, we make updates idempotent and monotonic. This example implements an idempotent state machine to avoid duplicate or out-of-order webhook updates, corrupting job state. The dictionary states encodes allowed progression so that succeeded or failed end states dominate earlier phases. The set name scene tracks processed event identifiers to drop exact retries instantly. The function applyEvent accepts one event, deduplicates via scene, loads the current job row from the job store, and compares numeric ranks to reject regressions. When valid, it updates status, an optional result in place. The events list simulates duplicates and a late regression to running that should be ignored. The printed final status shows the job remains succeeded, proving safe ordering. Next, we persist state so restarts are safe. This snippet persists reliable job state to SQLite, so callbacks survive process crashes and enable audits. The connection object opens an in-memory database for simplicity, and the cursor creates a compact jobs table keyed by job identifier. The helper upsert job writes the latest status with a timestamp and commits immediately, ensuring durability on each accepted event. A short loop walks the in-memory job store and saves each record once, mirroring what a webhook handler would do on every valid update. You can switch to a file path for real persistence without changing the function. The printed rows persisted confirms the number of durable job records. Finally, we wire everything into a secure request flow. This code wires a secure FastAPI webhook that authenticates, deduplicates, and saves results. The function secure reads the raw body and headers from requests, then calls valid sig to verify the HMAC signature and timestamp. When authentication passes, it loads JSON, applies apply event to enforce idempotent monotonic state updates, and only then persists via upsert job. This ordering ensures low latency acknowledgements while protecting against replay or disorder, and it centralizes incident debugging around a single flow. If you later add background tasks for side effects, keep the verification and state right in the request path. The printed secure handlers confirms the route is registered. To map this toy example to a production pipeline, swap the in-memory store for a real database and run the FastAPI app behind multiple workers. Keep verification and state updates synchronous in the request path. Then, dispatch non-critical work to background workers to avoid delaying acknowledgements. Recap: it is a secure webhook receiver that verifies signatures and records final job state. Use it when providers deliver asynchronous LLM results and you need reliable, auditable job updates. Caveat: timing and signature checks can reject slow callbacks, so tune the replay window carefully. Next step: replace the in-memory and ephemeral SQLite with a durable database and add timing metrics so you can measure callback latency and retry behavior at scale. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.